Okay, well, fingers crossed.
Okay, we'll just give it another few minutes for another minute for everyone to get on, and then we will get started. Yeah, feel free for right now to post in the chat and say where you're coming from, where you currently are. Oh, lots of messages coming in. Wow, all over. Korea, Paris, Mexico, San Francisco, Canada, Italy, India, New York, Portugal, Maryland, Texas, Taiwan, Toronto, California, Hungary, Tennessee, Washington, Las Vegas, Spain, Ireland. Wow, awesome. Okay, we'll get started now. I just want to go through a few logistics before we actually kick everything off. So to start with, welcome to the start of lecture 2. This lecture, excitingly, is going to focus on quantum computing in the abstract. As you learned last week about classical computing, we want to now have a parallel on, well, what is the difference between classical computing and quantum computing, and go into that into more detail. A few organizational points. The code of conduct. It is very important that everyone goes, if you've all agreed to the code of conduct, it's very important you adhere to it. Please make sure that you are being respectful of all of your fellow students, your administrators, and your academic staff members. Please particularly be aware of sending unsolicited messages on Discord or other platforms, whether that is to any of our team members or to your fellow students. In particular, make sure that you are not sending messages to a student of the opposite gender, where power dynamics can come into play and it can make certain individuals feel uncomfortable. So please make sure you're not sending messages to anyone unless they have asked you. And if they ask you to stop, please stop. If you are sending unsolicited messages and we get a code of conduct violation, we will be reaching out to you and giving you a warning. A few other points. Please, during lecture and labs, do not be spamming or posting continuously in the Q&A. Wait until the times that we actually ask for questions, and then you can post, but do not be posting continuously. Also, do not post answers in the chat. That we will have polls that you can do instead. It's incredibly unfair, though, to students, your fellow students who are trying to figure out what the answer is, to be posting. So only when we ask you, if we ask you to post the answer, then do so. Do not ask questions that are outside of the scope of the content. This is really important. We love how inquisitive and curious you all are, but it's incredibly important that you're making sure that, or that we're making sure that what the content that's being covered, it's been curated for what's going to maximize the learning that you need done. And so it's important that all the students understand the basic needs. And kind of last but not least, please be patient. Just like in a typical classroom, all of your questions are not going to be answered. We are doing our best to make sure questions are being answered. We have Piazza up, which is where you can post all your questions, and we have our TAs answering them, or your fellow students. We also are trying to answer as many questions during lab and lecture as possible that we think will really benefit you. But at the end of the day, you do also have to sit with this material for a while. And so don't just, the second you don't understand something, post in the question. Sit with it, review it, ask your fellow classmates, and we will try to get to as many of them as possible. A few other things, we will not be taking any more lab change requests. If you have not submitted a lab request yet, we ask of you, or you haven't submitted a lab, you must email us today if you do not, by the end of the day, send us an email with which lab you would like to be in, if you're not currently in one, you will be removed from the class. This has been over a week. We have given students to make sure that you're in the right lab. We have had over 2,500 lab submission changes. We really need you all to make sure that you're working on this and you're working with us, because it is such an administrative overload. So please make sure that those are taken care of. Also, we will be releasing Canvas later this week. So you will start to have access to Canvas later this week, and you will be able to submit your homework that is due this upcoming Saturday on Canvas. We will send more information in the Discord about this when Canvas is ready and when the homework is ready to be submitted. After this lecture, so at 4 p.m. Eastern time, we will be having a technology platform tutorial. You can just stay on this Zoom link, and we will walk through how to use Piazza, Discord, and Canvas, and also take questions about these. We will also be reaching out to everyone who has volunteered to be a student assistant, and we will send more guidelines this week. And once again, please do not be sending individual messages to any of your academic team or your administrative team members. If you have an individual question and it can't be answered on Discord or on Piazza, you need to email us at the student@qubitbyqubit.org email address. And with that said, I'm going to turn it over to Amir to get us started on quantum computing in the abstract.
Hi everyone, I'm very excited to be talking to you guys about quantum computing today. Of course, this lecture is going to be a little bit in abstract. The course is about quantum computing, and for this lecture, we're just trying to give you guys a taste of what's to come throughout the course, and maybe talk about some of the things that are cool about quantum computing without going into details necessarily. Okay, so with that being said, let's do a recap on what we talked about last week about classical computing. So last week, we talked about the binary representation and bits, and then we moved on to Boolean logic and the concepts of universality and reversibility. So let's start with a recap of what binary is. So in our daily life, we're used to using base 10 for counting, where our numbers start from 0 and go all the way to 9 before adding an extra digit. But there's no mathematical reasons to prefer, base 10, let's say, over any other base for that matter. And base 2 is one of the most important bases for performing computation. Base 2 is also referred to as binary. And what it really means is that there are only two possible values for every digit, 0 and 1. Now I can think of a 0 as a light bulb being off and a 1 as a light bulb being on. And what bit really stands for is a binary digit. So any number can be described using a combination of bits. We went through some examples from last week, some examples of that in last week. And all the operations that classical computers do basically happen by manipulating these bits. Next thing we talked about was logic gates. I'm not going to go too in depth about the different logic gates that we discussed last week, but what logic gates are some operation that map some input bits to some output bits. There are different varieties. So last week we talked about AND, OR, NOT, NAND, and XOR. And of course, there are multiple other logic gates that you can create using a combination of these gates. And we also discussed what a truth table is. We'll see the truth table again this week. But what a truth table tells us is, for a different set of inputs. So in this case, let's say if, the input of an operation, the first input is a 0, and the second input is also 0. It tells us what the output is based on those inputs. Then we talked about the concept of universality, which basically states that any computational operation can be made using a combination of NOT, AND, OR, and fan out. And this is a very powerful result, or a very powerful statement rather, because again, what it's saying is that these four operations that we have listed here can make anything we do, can make up anything we do with a computer, including listening on the Zoom call, playing Minecraft, and browsing the internet. Next, we talked about the concept of reversibility, which basically, is thinking about, given the output of a gate, can we determine what the inputs are? So if so, that's a reversible gate. And reversible gates preserve all the information in our system. Whereas non-reversible gates, where we can't tell what the inputs to a gate are based on the outputs, lose some information. And while for classical computing this is fine, for quantum computing, all of our gates have to be reversible because there is a penalty imposed by the laws of physics when you lose information. And that penalty can disturb our quantum information. So with that, let's talk about what the objectives are for this week's lecture. So we're going to be talking about quantum bits or qubits, quantum superposition, quantum gates, and quantum entanglement. So let's start with quantum resources for computing. And what I mean by that is some weird, quote unquote, weird behavior from quantum mechanics that we can exploit to solve problems that you can't solve classically. So the first one is superposition. Again, this is a picture of the Schrodinger's cat thought example that we talked about in lecture 0. The idea of superposition is that quantum objects can be in two states at once. So for example, if you have a quantum cat in a box, it can be both dead and alive at the same time. And you won't know if it's, or it'll stay this way until you actually make a measurement or an observation. And then in that case, it either becomes dead or alive. We'll talk about this in detail a little bit later. The next concept is quantum entanglement, where quantum entanglement is a quantum correlation between objects where the state of one quantum object depends on the state of the other quantum object, regardless of how far apart they are. And finally, there's a concept of quantum interference, where two quantum objects can interact with each other and either cancel each other out or amplify one another, similar to what you see with waves. And again, we will see examples of all three of these resources throughout this lecture. But the idea, again, is that these three weird quantum properties enable the design of quantum algorithms, which can compute in ways that classical computers cannot. And we use these resources to solve problems that we can't with the normal computers that we have today. Okay, so let's again do a recap of a qubit of quantum history, pun intended. So the idea of quantum computing came up in 1981. It was proposed by Richard Feynman, who was thinking of using a quantum system, i.e. a quantum computer, to simulate the evolution and behavior of other quantum systems. Now, the reason why he was thinking about this problem is because classical computers actually struggle with simulating quantum systems, and we will see why that could be the case. Whereas a quantum system, it's kind of like a natural thing to it almost. Okay, next, in 1994, Peter Shor showed that quantum computers can factorize large numbers efficiently. And this algorithm has massive implication when it comes to security. And in a sense, this kickstarted, the wide interest in quantum computing that has led to the advancement of the field today. In 1998, the first experimental demonstration of a quantum algorithm happened. So this algorithm was ran on a 2-qubit quantum processor. Again, nothing big, nothing too fancy, just showing that we can actually do quantum computing, using the systems that we have available. And then fast forward to 2012, we started having, quantum processors with few qubits, and we were able to detect, errors that were happening in these quantum processors. Now we still can't correct the errors, but we can find out if there's something wrong with our computation and act accordingly. And then in 2017, IBM put a quantum computer, their first quantum chip on the cloud, which allowed people from all around the world to access it. So again, this is something that we'll explore the IBM quantum experience today a little bit and run a few basic quantum circuits on it. But now, each of you has a capability of essentially going online, making an account, and running quantum algorithms on some small quantum computers, which is super cool. And then finally, in 2019, there was a Google supremacy a quantum supremacy demonstration by Google, which showed that quantum computers can actually perform a task that no classical computer can replicate within a reasonable amount of time. Okay, so with that being said, let's talk about quantum bits, or in short, qubits. And here we're really trying to think about, or get in the mindset of how do quantum computers compute? Okay, so again, let's talk about a bit first. So a bit can have two possible values, right? 0 and 1. That's just the concept of binary, and it's a bit. Now, a quantum bit, can also be 0, which we show with this thing called ket 0 and ket 1. And what this ket really means, it just said it indicates that we're talking about a quantum state. So if I put a 0 inside this ket, what that really means is that I'm talking about a qubit, not a classical bit. So for example, if we have the qubit by qubit, which is, it's a classical organization, and we want to make it quantum, we just put it inside a ket. By the way, this is not mathematically rigorous, like, putting QxQ inside a ket. But this is how quantum scientists show that we're actually talking about, something that's quantum rather than classical. Again, you just put it in a ket. And again, this thing, this symbol is called a ket. Okay, so let's now.
Can I ask a question about that?
Go
actually,
for it.
Amir?
Yes.
Okay, so I understand that the ket notation of, like, when you have is it just called 0 ket then for a qubit?
Yes, but I'll be calling it 0 throughout the lecture.
Okay, cool.
Yeah.
So when you have a 0 in kind of the ket bracket, it means that we're talking about a quantum state, or are we, the 0 actually is what the qubit represents? Could you go a little bit more into what this actually means?
Right, absolutely. So here, the thing you mentioned, they're basically synonymous in a sense that, a quantum state is, again, the state that a quantum object is in, and in this case, our quantum object is a qubit. So what this, ket 0, and again, I will be referring to this as 0 throughout the lecture, it just means that our qubit has a value of 0. And subsequently, what this, ket 1, or again, I'll be referring to it as 1, means is that our qubit has a value of 1. So now if I measure the qubit, or, if I open the box, look at the cat, or the qubit in this case, or in our course, I'm always going to get a 0, or I'm always going to get a 1. Again, this bit of it, this, just going from this way of going from bit to qubit is just a, simple extension almost. Now, the thing that we can do with these kets and with these quantum states, that's where the quantum magic comes into play, and we'll see. And again, there is, for those of you who are interested, there is, some mathematical, reasoning and mathematical meaning behind this ket, but that is not something that we worry about until next semester, when we, again, revisit all these topics, but, with a deeper math background.
Would it be possible for you to change the color of your pen to blue, or?
I can try.
Blue would be great.
Or, okay, blue.
Or black.
Let's try dark blue. Okay.
Awesome. Thanks so much.
Good?
Okay, you can keep going. Yeah, I understand now.
Amazing. Okay, so let's talk about quantum superposition. So what quantum superposition means is that quantum objects can be in two states at once. Again, the example of that is Schrodinger's cat, which, can be dead and alive at the same time. Or, for example, if I were a quantum object, I can be teaching this lecture and not teaching it at the same time. Now, saying this out loud sounds very counterintuitive and weird. And again, this is not something that we see in the classical world. This is a quantum behavior for objects. But now that we know that this behavior exists and what it means, let's talk about it a little bit in more detail with regards to our qubits or quantum bits. So again, for a qubit, when a qubit is in a superposition, it can be 0 and 1 at the same time. And that is different from, again, the normal bits, because normal bits can either be 0 or 1, whereas qubits can be 0 and 1 at the same time. And again, the way that we show this, using some basic math notation is, let's call the state psi our qubit. The reason why we use the letter psi is just convention almost. It's something that, if you learn a little bit more quantum mechanics about, like, this is what the letter that's most commonly used for showing a quantum state. But again, no, nothing's holding you back from, like showing your quantum state as, I don't know, let's say X, for example. Like, you could show your qubit with this symbol. What I'm getting at is that this symbol is arbitrary. The choice of psi is just because it's a convention that I'm used to. Anyways, so we can write a qubit, the state of a qubit, as, some coefficient alpha, which we will talk about, times the state 0, or times 0, plus some coefficient beta times the state 1, which again, we're going to talk about this alpha and beta in a bit. But you can see that the state of the qubit is a combination of 0 and 1 here. Okay, and the idea is that when we measure this qubit, it can no longer be in a superposition. We call this, the collapse of a quantum state, but as soon as we measure this qubit state psi, the state will collapse to either 0 or 1. So before we make any measurements, you can be in a superposition, but as soon as you measure, as soon as you look at your qubit, it has to choose to be either 0 or 1. And again, this idea is like analogous to what we've talked about with Schrodinger's cat, where the cat is both dead and alive until you open the box. But as soon as you open the box, the cat will either be instantaneously dead or alive. And again, this sounds counterintuitive because it is.
So Amir, this is one of the coolest things, I think, as I've been learning quantum computing, the fact that a qubit can be like 0 and 1 at the same time, but at the same time, when you try to measure it, it has to be one or the other. What does this pose any problems for like quantum scientists when you're doing your work, or how do you solve this kind of measurement issue?
So it's actually not a measurement issue. This is just how the world works, and it is interesting in the sense that again, this is something that we will touch on more next semester when we talk about quantum mechanics. But the evolution, like how a quantum state changes, is actually completely deterministic. So we can, I can, like, if you give me the quantum state, like, my qubit at time 0, and tell me, like, some operations are acting on it, I can tell you exactly what the superposition is as a result of all those operations after some time. Now, the randomness only comes in when you measure, again, when you collapse a wave function. But the dynamics in between is actually completely deterministic. And again, this was fascinating to me when I was learning about quantum mechanics, because like when you think of quantum mechanics, you think everything's random, everything's weird. But actually, like, if you look under the hood, a lot of the things are determined by the laws of physics. It's just that there are some bits and parts that are random in a sense, and measurement is one of them.
Awesome. And then could you just explain again the equation that you have here for superposition? We're getting some questions about, are these numbers complex? Is this just used in theory or in actually describing how the world works? So would be great if you could go a little bit more.
Yeah, absolutely. Again, so some of these questions, we'll get the answer to in a couple of slides. But one question that I'm not answering, for example, and I guess was just asked is, what are these numbers? And so A, or alpha, and beta are both complex numbers. Now, if you don't know what complex numbers mean, don't worry about it. This is something that we will learn about in this course, and we will revisit these from a more mathematically rigorous background. Just know that, like, these are two constant values. And actually, let me move on to the next slide, and I feel like I will be answering some of those questions. Okay, so again, let's talk about the measurement. So if my qubit state is, alpha times 0 plus beta times 1, once I measure it, the quantum state will of the qubit, the state of the qubit, will either be 0 or 1. Okay, so what determines the probability of measuring a 0? Well, this coefficient in front, this alpha in front that I had, so the whole point of it is that alpha squared gives me the probability of measuring the qubit in state 0. And similarly, beta squared, well, beta amplitude squared, gives me the probability of measuring the qubit in the state 1. And what does that mean? So, okay, so we've talked about how the qubit has to be, or is either, like when I measure, it's either in the state 0 or 1, and there's nothing else possible. So that being said, the probability of the qubit being in 0, or the probability of measuring the qubit to be in 0, plus the probability of measuring the qubit being in 1 has to add up to 1, because that's how probabilities work. So based on this, I can conclude that alpha squared plus beta squared, and I don't know why these spikes happen, but let me try to fix it. Okay, alpha squared plus, again, this is a beta squared, has to be equal to 1. And this is the only physical restricting thing about alpha and beta. So as long as alpha and beta obey this relationship where the square of them adds up to 1, they can be any number. And in fact, again, actually, let's maybe go on one more slide. Let's look at an example. For example, if I want a 50-50 superposition of 0 and 1, meaning, when I measure the state psi, I get 0 with 50% probability and 1 with 50% probability, my quantum state will look like this. So again, here, I'm going to write it out here. So alpha up here is square root of 0.5, and beta is square root 0.5. So alpha squared, which gives me the probability of measuring 0, is 0.5, which is 50%, and beta squared, which gives me the probability of measuring the qubit in the state 1 to be 1, is also 0.5, which is 50%. Now let's look at another example. So what if I want a 90-10 superposition, where, when I measure the qubit, I get 0 with 90% probability and 1 with 10% probability. Then the quantum state will look something like this. And again, just to write it out similar to the example above, here alpha is equal to square root of 0.9, and beta is equal to square root 0.1. So alpha squared, which gives me the probability of measuring the state 0, is 0.9 or 90%, and beta squared, which gives me the probability of measuring the state 1, is 0.1 or 10%. Okay, so far so good. So maybe let's look at another example. So I'm going to ask you guys to play with this, think about this for 30 seconds, and then we'll do it together. So what if I want a 75-25 superposition. My pen's acting weird again. So what would my quantum state look like in that case? So psi is equal to what?
Amir, just so everyone's clear, when you say, for example, 50-50 superposition, that means a 50% probability of it reaching 0, or a 50% it's 1. Mm-hmm. Is that correct? So in the 75-25, it would be 75% 0.
Yes.
Like it would be, okay, awesome.
Yes, so maybe actually that's a good point. Let me just, I'm just gonna, maybe write it up here. So this is probability of 0, and this is probability of 1. Okay, so let's write this together now. Okay, so I said that the probability of being in zero is 75 or 0.75, 75% or 0.75. So the coefficient in front of zero, which is again the alpha that we were talking about, will be square root of 0.75 times zero. And the reason for that is because if you square this coefficient, you get 0.75, which is the probability of being in zero. And I guess subsequently, the probability of being in the state 1 is 25%. So the coefficient in front of the 1 state should be square root of 0.25. Okay, sounds good? So let's practice with this a little bit more. Now let's do things the other way. So if I give you a state, a quantum state psi, which is equal to 1/3 or square root of 1/3 times 0 plus square root of 2/3 times 1. Can you tell me what the probability of 0 is and what the probability of measuring a 1 is once you measure this qubit? Again, take 20 seconds, think about it, and then I'll write the numbers down.
Amir, I want to make a quick announcement as well. Folks, please remember the ground rules that were described at the beginning by Kira about the chat in the Q&A. There are now almost 600 questions in the Q&A, and we will absolutely turn it off if students cannot respect the fact that Amir is continuing to teach. So many of the questions that you're asking are being explained by Amir or will be in the lecture. So please focus unless you're asked to provide questions. Sorry, Amir.
Thanks, Rachel. No, all good, all good. Okay, so this is similar to what we talked about earlier. So the probability of being in the state 0 is just a coefficient in front of 0, squared. Well, rather the amplitude squared, but we're not going to worry about that for now. So therefore, probability of being in the state 0 is 1/3 for this quantum state. And the probability of being in state 1 is 2/3. And again, just as a sanity check, if you add these two numbers together, if you add these two fractions together, you get 1. So I'm not breaking the laws of probability with these quantum states. So now the interesting thing is that there are a continuous set of superposition states. States. What do I mean? So let's say we have, okay, this is the line. Let's say 0's here on top, and then 1 is here on the bottom. I can be anywhere on a circle of radius 1 from the center. Let's say this is the center point, and this is radius is equal to 1. With my quantum states. So for example, I can have a 90-10 superposition. So again, 90% measuring 0, 10%, I'm gonna fix this, 10% measuring 1, which would put me closer to the state 0. Or I can have a 50-50 superposition, which again, puts me exactly halfway in between 0 and 1. Or I can have a 25-75 superposition. Again, 25% probability of measuring 0 and 75% probability of measuring a 1, which puts me closer to the state 1. Now, we're not going to talk about what's exactly motivating this or what are the caveats of this representation, but this is something that you will see further on in the course. And now we're talking about being on a circle, but turns out in reality, like the qubit can actually be represented using a sphere. Now we're not going to talk about why that's the case right now, but that is something that we will get to later on in the course. Anyways, the whole point is that some circle or a sphere might be a good way of visualizing the state of a qubit, where if you have a higher probability of measuring 0, you will be closer to the top pole, to where the 0 pole is, And if you have a higher probability of measuring a 1, you will be closer to the bottom of this circle or sphere where, the 1 state is. And of course, if you're exactly on the top, you're going to measure 0 with 100% probability. So every time you measure, you're going to get a 0. And if you're on the very bottom, every time you measure, you're going to get a 1 with 100% probability. Okay, so with that, if there are, I guess if Kira doesn't have any comments, let's move on to quantum gates. So the approach that we're going to have with quantum gates is going to be similar to what we did with classical gates last week. So there are 3 single qubit gates that I want to talk to you guys about today. Of course, there are many more, but no, these 3 are the ones that we've chosen for this brief quantum computing lecture. So there are the X gate, the Z gate, and the Hadamard gate. So let's see what they are. So the X gate, which I'm going to show as X, or sometimes we show it as sigma X, is a bit flip. What does that mean? So if I apply this X gate to the state 0, and this is how we show gate applications in quantum mechanics, then I get the state 1. Or if I apply this X gate to the state 1, I get the state 0 as an output. Now, if you're like me, you might look at this for 30 seconds or a minute, and this might remind you of a gate that we've seen for classical computing. In fact, this is this X gate, which is a bit flip gate, is analog to the NOT gate almost in classical computing. Yeah, if I enter a 0 here, it outputs a 1, and if I enter a 1, it outputs a 0. So with that, let's go back to our good friend, the truth table. And let's try to write the truth table for this quantum gate. So, okay, if I have, let's call this input and output. So if the input is a 0 state, I get 1 out. And if the input is a 1 state, I get a 0 out. And also another way of showing these operations that I have up here in circuit language is, so this is the schematics of this X gate. So I can feed it a 0 here, and it'll output a 1 over here. These are all different ways of representing this gate. But the takeaway message is, again, the X gate acts similar to a NOT gate. So if I feed it the quantum state 0, it outputs the quantum state 1. And if I feed it the quantum state 1, it outputs the quantum state 0. Okay, let's move on to the next gate. So this is a Z gate, or we sometimes show it as sigma Z. And this is a phase gate. Now, again, if you're thinking in terms of classical computing, you might ask, what is a phase? Well, turns out there's actually no analog for this operation in the classical logic gates that we've talked about, at least in this course. So if I apply a Z gate to the state 0, it doesn't do anything. So Z gate applied to state 0 just outputs the 0 state. Now if I apply the Z gate to the state 1, it adds a negative sign to the front. Okay. So the Z gate applied to the 1 state gives me negative times the 1 state. And again, let's write a truth table for this. So, okay, input, output. So again, possible inputs are 0 state and the 1 state. And if I input the 0 state, I get the 0 state out with no changes. And if I input the 1 state, I get the negative 1 state out. So negative 1 times the 1 state. Now, you might be asking me, so what is the significance of this negative sign or this phase? And I've danced around that question a little bit in this lecture because, again, we will need to get a little bit into the math to see the significance. But just know that, this negative sign, which again has no classical analog necessarily, will play a role when it comes to some quantum algorithms. And again, we will see like, some places that this could make a difference a little bit later in the lecture. But again, we will be talking about this in more detail throughout the course. Okay, and then the final single qubit gate that I want to talk about is the Hadamard gate. Now, Hadamard is the name of a famous mathematician. And what the gate does is that it creates a 50-50 superposition from the 0 and the 1 state. Okay, so let me write down what this gate does then in a little bit of a more like using the notation we've learned so far. So if I apply this H gate to the 0 state, I get square root of 0.5 times 0 plus square root of 0.5 times the 1 state. And if I apply this Hadamard gate to the 1 state, I get a square root of 0.5 times the 0 state minus, and again, this is the big difference here, a square root of 0.5 times the 1 state. So again, we still have a 50-50 superposition regardless. So if I measure the state, if I measure the state of the qubit, if I measure the qubit applying a Hadamard to 0 or to 1, and I measure it afterwards, I still get 0 with 50% probability and 1 with 50% probability. But the big difference here is, in the sign that's between the the elements of the superposition. Now, again, we will see the significance of this sign a little bit later, but just for now, just know that it exists, and we'll see, when it comes into play. And
Amir,
yes.
Sorry, could you take a few minutes and take a step back and go over just the purpose of gates again, and in particular, what the purpose of quantum gates are? And then I have a few follow-ups, but that would be a great place to start.
Okay, so the purpose of quantum gates is to do quantum computation. So again, to draw an analogy to classical computation, in classical computation, we had bits and we had logic gates. The bits are, your input states, and then the computation happens with a combination of these classical logic gates or classical gates. Now in quantum computing, the analog for bits are qubits, quantum bits. Now, of course, I have some special quantum properties that allows you to do more things than you can with a classical gate, or with classical bits. And quantum gates are just quantum operations that you mix and match to do quantum computing.
So these gates, in essence, Hadamard, the X and Z gates, these are kind of allow quantum computation to happen.
Yes. So again, I guess I don't talk about it here in detail, but we talked about universality for classical computing, where using a set of gates, you can create any operation that your heart desires. A similar concept also extends for quantum computing. So you're using a certain set of 1 qubit gates and something like some 2 qubit gate, which we will talk about later. You can do any quantum computing operation whatsoever.
Awesome. And could you just go through again? I know the first 2 gates are quite simple, but if you could just go through on, either the right side or go back to them and just go over what the differences are between each one again, I think that would be great. Just so we're learning 3 new gates. So I just want to make sure everyone's very clear on them.
Yeah, so the first one, the X gate, just flips the state of the qubit. Again, it's very similar to the classical NOT gate, where if you feed it 0, it gives you 1, and if you feed it a 1, it gives you a 0. Now the second one, the Z gate, is a little bit different. So if you apply the Z gate to the 0 state, it doesn't do anything, just outputs the state 0. Whereas if you apply the Z gate to the 1 state, it adds a negative in front. So it outputs, -1 times the 1 state.
Why does it do that?
we will need more quantum mechanics and linear algebra for me to be able to answer that question. But again, once we have the tools, this becomes very clear. And then the last one, of course, is the Hadamard gate, which, regardless if I feed it a 0 state or a 1 state, it creates a 50-50 superposition. Now, the big difference is that, if I apply the Hadamard gate to the 0 state, it gives you, square root of 0.50 plus square root of 0.51. Whereas if I apply it to the 1 state, it gives me square root of 0.50 minus square root of 0.51. And again, why that's the case, we will revisit this, and it will be clear why that's the case. Just for now, know that this is the case, and we're gonna try to do some cool stuff with it. Okay, so let's go back to our good friend, the truth table again. And what I'm gonna ask you guys is, while I'm setting this up, think about what the truth table for this gate looks like and write it down. Okay, so again, the 0 state and the 1 state both result in an equal superposition of 0 and 1. So now I'm going to write this down a little bit differently. I'm going to write this as the state 0 plus the state 1 divided by square root of 2. And again, that is the 1 over the square root of 2 is the same thing as square root of 0.5. And in this case, I'm going to show this as 0 minus 1 divided by the square root of 2. And again, just to recap, the Hadamard gate creates an equal superposition when you feed it the 0 or the 1 state. So if we want to think about it conceptually, it might be a good way to start our quantum algorithms in general. If we start with, some input states 0 or some initial state 0, a good strategy would be to just put everything in an equal superposition by applying Hadamard. Now, again, we will see this in the course, and if this doesn't make sense to you immediately, that's fine. We will revisit this multiple times. But again, just to give you a sneak peek of what's ahead, the Hadamard gate is very central for quantum algorithms. Okay, so with that being said, let's take a 10-minute break. So right now it's 2:48 Eastern Standard Time. Let's be back by 2:58. And then we will see these gates in action on the IBM quantum experience before we move on to the next section. Okay, everyone, I think that was it for our 10-minute break. So before getting to some questions, let me just say a quick recap of what we've talked about. And then we're going to take some questions, and then we're going to see some of these quantum gates in action using the IBM quantum experience. So first things first, we talked about, again, what are quantum bits? How do they relate to classical bits and what's different? So, in that context, we talked about how, classical bits are either 0 or 1, whereas quantum bits can be in a superposition of both 0 and 1 at the same time. And then we segued into talking about some quantum gates. So we talked about the quantum bit flip gate, or the X gate, which flips the value of 0 to 1 and the value of 1 to 0. Then we talked about the Z gate, which is a phase gate. And the Z gate applied to 0 doesn't change anything, whereas the Z gate applied to the 1 state adds a -1 in front of the 1 state. We're going to see the significance of that gate throughout the course, but that is something that has no classical analog, at least with the stuff we've talked about. And finally, we talked about the Hadamard gate, which can be used to create, this 50-50 superposition state when we apply to a 0 state or a 1 state. So with that, let's maybe answer some questions, and then we can see things in action using the IBM quantum experience.
So first off, to everyone, I want to make an announcement about the captions. Closed captions are available. You have to go to the bottom of your screen and change the settings. On mine, it's live transcript, and you can click on that and enable captioning. But you have to do that on your own individual device. But we do have live captioning going, and you can view it live and in real time. And then that's it in terms of announcements. In terms of questions, Amir, we're getting a lot of questions about how do you actually know the probability of, of it either being 0 or 1? And can you change the probability? If so, how?
Yeah, so that's a great question. So I guess we talked about the, things on the mathematical end, right? How if I, write down the math equation for a quantum state, you can tell me what the probability of being in 0 is versus the probability of being in the 1 state is. And that's just the probability of being in the 0 state is just the amplitude in front of the coefficient in front of 0 squared. And then the probability of being in the 1 state is just a coefficient in front of the 1 state squared. Now, what is the physical significance? So what does this actually mean, in the language, without the math? So, I guess this was another question that I also saw. So there is no physical reason why we square these amplitudes. This was almost like the footnote of one of the seminal quantum papers that basically was like, okay, what the probability of getting 0 is amplitude squared. The probability of getting a 1 is also the amplitude in front of the 1 state squared. So there's no physics behind that, but to answer Kira's second question, in quantum computing, we are able to engineer, well, I guess in theory, it's a little bit more difficult in lab, but we, in theory, are capable of engineering, any superposition state that we want. So, we can engineer a quantum superposition that is, 99% of the time 0 and, 1% of the time 1. Or we can easily engineer these quantum superpositions that are 50% of the time 0, 50% of the times 1. The same way that we can engineer a quantum state that's purely 0 and a quantum state that's purely 1. We are going to talk about how we do that. We have a full lecture on actually, the implementations of quantum computing. But I guess to give you guys just a brief overview. So I work with superconducting qubits for my research. And the way that we make these transitions, we create these superposition states, is that we apply a microwave pulse with different, we apply microwave pulses to our qubits, and we can change the length of these microwave pulses to determine, basically get the superposition state that we want. It's like, if the time needs to be zero, like if we need to apply, 0 seconds of, or not 0 seconds, let's say, 0 units of time to be in the 0 state and 1 unit of time to be in the 1 state, we can apply, we can keep our microwave pulse on for, 0.99 units of time to be in the, 0 state with 99% probability and the 1 state with 1% probability. Or sorry, rather the other way, 99% of the time in the 1 state, 1% of the time in the 0 state. And again, this is something that is a little bit more complicated, and we are going to talk about later in the course. I just want to let you guys know that there is some meaning to these superposition states, and actually we are able to create different superposition states in real life, not just on paper. So I guess I can just go through some of the other questions that I highlighted on my notes. So some people ask, what do I mean by a quantum object? A quantum object is just anything that is small enough that kind of acts and behaves based on the laws of quantum mechanics. So that's all it means. Now this quantum object can be an electron, or it can be a molecule, or it can be a qubit. Actually, for the rest of the course at least, we talk about qubits. And it turns out you can use electrons, for example, as qubits, but that's something that we talk about later on. But anyways, just to again address any confusion, when I talk about quantum objects, I simply mean something that behaves based on the laws of quantum mechanics. Anything I missed? I guess if not, now let's see these quantum gates in action using the IBM quantum experience. So again, this is the circuit composer interface for the IBM quantum experience. Here, this top line represents a qubit, and then this bottom line represents a classical bit, which is a result after we make a measurement. So, and here we can see the measurement probabilities that we talked about. And over here we see the state vector, which is, if you guys remember, when we were writing psi is equal to alpha 0 plus beta 1, that is what the state vector is. So with that, let's play around with this a little bit. So if I don't do anything to my qubit, it always starts in the 0 state. And that is just how quantum hardware works almost. All the qubits are usually initialized to the state 0. Now I can grab this X gate that we talked about. And again, an X gate flips the 0 state to the 1 state. So let's see if that actually happens. So apply this X gate to the state 0. And yep, I get the 1 state, or state 1, with 100% probability. And then I don't get any probability on state 0, which makes sense. Now, okay, so now at this point, I'm in the 1 state. Now, what happens if I apply another X gate? Actually, can we do the poll now? There's a poll. Okay, so yeah, let's maybe take some votes. So if I apply another X gate to this 1 state that I've prepared, what do I get? Here, the numbers are coming through. We have 60% now. Okay, amazing. So most people have voted. And it seems like the consensus is that we're going to get a 0 state with 100% probability. So let's check it out. So, okay, I'm applying another X gate now to my qubit 1. And yep, we get the 0 state with 100% probability, and then nothing on the 1 state. So again, we talked about this. This is what the X gate does. Okay, so now that we got that out of the way, let's play a little bit with the Z gate. Okay, so right now I'm applying the Z gate, or actually rather, I'm not going to apply that yet. I'm going to maybe do another pull. So what happens if I apply, if I drag and drop this Z gate on the 0 state? What do I get? Yeah, for those of you who've submitted the poll for this question, think about what's going to happen if I apply the Z gate to the 1 state. And again, for that, actually, I guess we'll get there. We'll get there. Okay. Yeah, I mean, the overwhelming majority of the people are saying that if we apply a Z gate to the state 0, we just get 0 with 100% probability. And that is the definition of the Z gate. Okay, now let's try this with the 1 gate. So, let's try this with applying the Z gate to the 1 state. So first, the way that I can make a 1 state when I start off from 0 is applying an X gate. So I apply the X gate to my qubit now, and all of a sudden I'm in the 1 state. Now there are 2 different questions I want you guys to think about as you're answering this next one. So what happens if I apply a Z gate here now? So there are 2 different things you should think about. First, what happens to the measurement probability? Like if I measure the qubit, what am I going to get? And then what happens to the state vector of the qubit? I'll give you guys 30 seconds to think about this. And again, let's do another round of polling, and then I will go through it. Okay, I think we've had enough people answer the poll. So let's try it. So I have the 1 state, and now I'm applying a 0 gate to it. Okay, so there are 2 different things to look at now. The first one is the measurement probability. So if I apply the Z gate to the 1 state, I still measure 1 with 100% probability. That makes sense. But now let's see what happens to my state vector. So if you guys noticed, this color changed. And again, ignore the phase angle for now. We're gonna see the significance of that later. But now what the state vector is telling me is that I'm getting the negative times 1 state, right? And again, if you guys remember the reason, so when we apply the Z gate to the 1 state, we get -1. And the reason why when we measure, we get 1 with 100% probability is because in measurement, we actually square the coefficient in front of the 1 state. And -1 squared is just 1, which translates to 100% probability of getting it. So yeah, the answers that we got from the poll were, again, in a superposition of the 1 state and none, which are, both in a way correct. So I guess the right answer would technically have been none, because that is a quantum state, but since you can't measure that -1, One's also fair game. Okay, and for the last part, let's try applying a Hadamard gate. So again, let's do another round of polling. What happens if I apply a Hadamard gate to the 0 state? Okay, that's good. So yeah, again, an overwhelming majority of you, I think, have it nailed down. So if I apply Hadamard to the 0 state, I get 0 with 50% probability and 1 with 50% probability. Now, while we wait, or I should rather, let me maybe run this on an actual quantum hardware. So what we see here is just a simulation of what the quantum hardware does, but let's actually run it on, on a quantum computer and wait a little bit and see what the result is. Okay, let me see. How do I? Oh, sorry. Yeah. Okay. And to run things on quantum hardware, of course, you have to add measurements. Because that's how quantum computers work. You actually have to tell it when to measure. And as you can see, the status of my quantum hardware run is being updated on the side. So while we wait, before we check the result of that, now what happens if I apply a Hadamard gate, and this superposition gate that we talked about, to a 1 state? So again, just to recap or review rather, I start with the state 0. I apply an X gate to go into the state onto state 1, and then I apply a Hadamard gate. Oops. Well, I don't want to spoil the fun, so let's just assume nothing happened, and you guys fill the poll and tell me, what do we get? Okay, amazing. Yeah, it seems like most of you have it nailed down. So if I drag this Hadamard gate down here now, I get the 0 state with 1 over square root 2 amplitude, and then the 1 state with negative 1 over square root of 2 amplitude. So the right answer was 0 minus 1 divided by square root of 2. And now if I measure that, I still get 0 with 50% probability and 1 with 50% probability. And again, that's because we're squaring the amplitudes in front of our quantum state. So 1 divided by square root of 2 squared gives you 1/2. And also negative 1 divided by square root of 2 squared also gives you 1/2. And again, that corresponds to 50% probability of measuring 0 and 50% probability of measuring a 1. Okay, so let's see now what was the result of the this Hadamard gate that we ran on our quantum hardware. So again, we applied a Hadamard gate to the 0 state. Okay, so we get 0 with almost 50% probability and 1 with, again, almost 50% probability. And again, the reason why this is not exactly 50-50 is because our quantum computers are filled with errors, of course. And this deviation in probability is caused by some of the errors that are natural to quantum hardware. Okay, and let's try one last thing. Actually, I think the poll will be very valuable here. So let's say I start with the 0 state and I apply Hadamard gate. So I put my quantum state in an equal superposition of 0 and 1. Now, what happens if I apply another Hadamard gate? So yeah, let's again take 30 seconds, fill a quick poll, and we'll see. I'm quite curious to see what you guys think. Okay, so just looking at the poll results, we have the answers are almost spread out between getting a 0 plus 1 divided by square root of 2, and none. So let's see, let's try it out. Okay, so if I apply 2 Hadamards to 0, then I end up in the 0 state with 100% probability. And this is kind of amazing. I mean, we'll talk about this a little bit further down, but just think about if you were talking about a coin flip, right? And again, we will revisit this in a few slides. If I flip a coin twice, what would the probability of getting heads be, and what would the probability of getting tails be? So think about that, and think about why this might be a little counterintuitive to the notion of probability that we're used to, at least. Okay, with that, I want to continue to the rest of the lecture. So I'm going to stop sharing the quantum experience, and I'm going to start sharing the slides again. Okay, so let's talk about applying quantum gates to a superposition state. So quantum gates apply to each state of the superposition separately and in parallel. What do I mean by that? Let's look at an example. So let's say we apply the quantum gate X to state psi. And again, I should rewrite that up here, but psi here is equal to alpha times 0 for again, some coefficient alpha. We don't worry about what alpha is in this case. And beta 1, again, for some coefficient beta. And just as a reminder, X applied to 0 gives me 1, and X applied to 1 gives me 0. Okay, so if I apply the X gate to the superposition, it's the same as me applying the X gate to every state individually. So now I have alpha, the coefficient alpha, moving it out, and then I have the X gate acting on 0, and then I'm moving out the coefficient beta here, and I have the X gate acting on 1. Well, based on this, what do I expect? So, and again, I have these relationships on the side, relations on the side if you've forgotten. But then X gate applied to the 0 gives me a 1, and then the X gate applied to a 1 state gives me a 0. So then the result of this is alpha times the 1 state plus beta times the 0 state. And again, let's take a step back. So when I applied this quantum operator to the state, it essentially flipped both the qubits at the same time. And each of them separately and in parallel, or at the same time. So let's look at another example. So another gate that we talked about earlier was the Z gate. And again, let me just write, the Z gate on the side here. So if I have Z, or what the Z gate does rather, if I apply the Z gate to 0, I just get 0 out, nothing's changed. But if I apply the Z gate to the 1 state, then I get a -1. Okay, so now let's do some practice with that. So what happens if I apply the Z gate to the 0 plus 1 over square root of 2, the equal superposition state? Maybe take 30 seconds, think about this, and then I'll write it out. Actually, maybe we should try the poll for this as well. So I'm relaunching the poll now. Yeah, tell me, what do you think the answer is? And yeah, as you're sending in your poll results, I'm gonna start going through this. So, okay, again, what I talked about is that, the quantum gate acts on every element of the superposition separately. So, I can rewrite this as, again, a square root of 2 on the bottom, a Z gate here acting on top, plus another Z gate here acting on the 0, and another Z gate acting on the 1, right? And I mean, again, just based on the poll results, it seems like people are on the right track. So the Z here acting on 0 gives me the 0 state, nothing will change. And then the Z here acting on the 1 state gives me a -1 divided by, of course, square root of 2. And let me end the poll. Okay, now let's try out the other gate we learned about today. So what if I apply a Hadamard gate to the 0 plus 1 divided by square root of 2 state? And I'm gonna open, we restarted the polling, which is amazing. And let me just write the definition, or write what the Hadamard gate does here on the side. And again, you guys can continue working on this. So the Hadamard gate acting on the state 0 gives me 0 plus 1 divided by square root of 2. And then the Hadamard gate acting on the 1 state gives me 0 minus 1 divided by square root of 2. Okay, so let's go on. And again, feel free to respond to the poll. I'm going to start doing this piece by piece. Okay, so I can write this again similar to what we had up there for the Z gate, and also for what we saw for the X gate. I can rewrite this as the Hadamard acting on the 0 state plus the Hadamard. Okay, I don't know why my stylus is not having it today. Plus the Hadamard acting on the 1 state, divided by square root of 2. So now let's do this piece by piece. So I'm gonna pull out a 1 over square root of 2. Okay, so 1 over square root of 2 here. So what happens when I apply a Hadamard gate to the 0 state? Well, I have the mapping here. So I get 0 plus the 1 state divided by square root of 2. And then when I apply this Hadamard to the 1 state, I get 0 minus 1 divided by square root of 2. Okay, so let's see. So let me rewrite this. So okay, I'm going to pull another square root of 2 out. So I have 1/2, then 0 plus 1 plus 0 minus the 1 state. Okay, so let's see. So I guess I have 2 zeros here, and then there's a 1/2 over there, so I get the 0 state. But now here I have a +1 state and a -1 state, and these two will cancel each other out. So if I apply a Hadamard gate to the superposition state, I end up with the 0 state. And actually, these 1 states canceling each other out is an example of quantum interference. We're going to talk about this a little bit more in a couple, maybe actually even on the next slide. I'm not sure, but anyways, just keep this in mind. Actually, and also most of you got this right on the poll, so I'm very impressed. Okay, so with that, what is the difference between a coin flip and a quantum superposition? Because again, if you think about a quantum superposition, right? Like if you measure a 50-50 superposition, you get 50% 0, 50% 1. And that is all, like, you might think to yourself, oh, well, that's the same thing as if I were to flip a coin, right? And call the head 0 and tails 1. So, okay, let's do this piece by piece. So if I do a coin flip, if I do one coin flip, if I have a coin and I flip it once, then I get 50% heads, which I'm going to show by H, and 50% tails, which I'm going to show by T. Now again, heads and tails are binary. You can think of them as 0 and 1, but let's just stick with this notation for now. Now, if I take the same coin, maybe not look at what the result was, and then I flip it again, then what is the probability of getting heads? Well, I mean, it doesn't matter what the initial state of the coin was. Regardless, if I flip it again, I still get 50% probability of getting heads and 50% probability of getting tails. So if I have a classical coin, a normal coin, if I flip it twice, I still get heads with 50% probability and tails with 50% probability. Now, what if I have a quantum superposition? So, let's say I start with a 0 state and then I apply a Hadamard gate and I measure this state. So 1 Hadamard gate and then I measure it. I get, 50% probability of 0 and 50% probability of 1. So far, again, you might think to yourself, well, this is just like a coin flip. What is the difference? Now what happens if I apply 2 Hadamard gates? And then measure. Well, now we actually just did this example. We saw this example in the IBM quantum experience, but also, if you go back 2 slides, this like state that we apply the Hadamard to is actually, the result of a Hadamard acting on 0. Okay, yeah, we did the work there. We see that we get 100% probability of getting 0. And 0% probability of getting a 1 due to quantum interference. So just to recap, the result of 2 classical coin flips is 50% 0 and 50% 1. Or, you can call it 50% heads and 50% tails. Whereas the result of 2 Hadamard gates is 100% of the times measuring the 0 state or being in the 0 state. And again, this is the concept. This concept is quantum interference, where the states involved in a quantum superposition can either cancel each other out or amplify each other. And in this case, the zero states the zero states amplified each other, and the one states canceled each other out. So again, I guess this color probably doesn't show well on here, but let me do a quick color change. So I had 1/2 0 plus 1/2 0, which gave me just 0. And then I had 1/2 1 minus 1/2 1, which canceled each other out and just gave me 0. So that is an example of quantum interference. And again, we will be coming back to this again in the course, and this quantum interference is a backbone of all quantum algorithms. So the general strategy for quantum algorithms is that you want to start with an equal superposition of all possible answers, and then use quantum interference to cancel all the wrong answers out and to amplify the probability of getting the right answer. That's in a nutshell. Okay, so why are quantum computers faster? So if I have a single qubit, I can be in a superposition of two states, 0 and 1. Now, if I have two qubits, I can be in a superposition of two states, 0, 0, 0, 1, 1, 0, 1, 1. Now, you might be looking at this and might be asking, oh, can we have, two like qubits in one of these brackets? The answer is yes, and we're going to discuss that in a moment. And if we have 3 qubits, we can be in a superposition of 8 states. And if we have 4 qubits, we can be in a superposition of 16 states. So in general, if we have n qubits, we can be in 2 to the power of n superposition states, all at the same time. And each operation that we do, as we talked about, acts on all the elements of the superposition at the same time. So again, let's think of this in terms of classical computing and quantum computing. So for classical computing, if you want to change 16 states, you have to apply 16 different operations. Whereas in quantum computing, what we talked about based on this quantum parallelism, if you want to if you want to change these 16 superposition states, you can do that with a single operation. Now, it depends a little bit on what you want your change to be, but a single operation will act on all 16 states. And that is where the intuitive power of quantum computing comes from almost. And this leads to the notion of quantum supremacy, where a programmable quantum device can solve a problem that no classical computer can solve in any feasible amount of time. And again, this concept, again, the things that give rise to that, of course, is superposition, and the fact that we can use quantum interference to cancel out the wrong answers of the superposition and amplify the correct answers. And this one other concept, the last concept that we're going to talk about, called quantum entanglement, which is some correlation between the qubits that we can use to amplify the power of our quantum computers. Okay, so far everything we've talked about only was for 1 qubit. Now let's talk about a case where we have 2 qubits. So I'm going to call these qubits A and B. And the way that you can show them is, each qubit gets its own line in the circuit. So this is qubit 0 and qubit A on the top line and qubit B on the bottom line. Now, I can have the 0, 0 states, which I can either show in the same bracket like this, or in the same ket like that, or I can, do 2 separate kets. These are equivalent, and we're probably going to go back and forth on using these. And what this means is that qubit A is in the 0 state, and qubit B is also in the 0 state. Now, the next possible combination is 0, 1, which again, I can either show in the same ket or 2 separate kets. And what that means is that qubit A is in the 0 state and qubit B is in the 1 state. Similarly, I can have 1, 0. And again, here qubit A is in the 1 state and qubit B is in the 0 state. And finally, I can have the 1, 1 state can be represented like this. And here qubit A is in the one state and qubit B is also in the one state. Now that we have that definition in the bag, let's talk about a 2-qubit gate. I'm going to talk about the C0 gate. So C0 stands for control node, and it operates as follows. So if the control qubit, which is the top qubit, is a 0, does nothing to the bottom qubit. Now, if the control qubit, the top qubit, is a 1, it flips the target qubit or the bottom qubit. Okay, so maybe let's try to write a truth table for this. And again, I'll give you guys 30 seconds to try to write this yourself, and then we'll go through it together. Okay, so over here in the input and the output, I've broken down my 2 qubits. So C is the control qubit and T is a target qubit. So let's go through it line by line. So if the control qubit is 0 and the target qubit is also a 0, well, since the control qubit is 0, we don't do anything to the target qubit. So we get the 0, 0 state out. Now, if the control qubit is, again, a 0 and the target qubit is a 1, nothing happens because the control qubit is a 0, so I get the 0, 1 state out. Now, what if the input, on the input, the control qubit is a 1, and then the target qubit is a 0? Well, this gate doesn't do anything to the control qubit, so I get a 1 out anyways on the control. But now, since the control was a 1, I flip the target. So I go from 0 to 1. So again, an input of 1, 0 gives you an output of 1, 1. And now if my input is 1, 1, since the control qubit has a value of 0, we flip the target qubit. So this gives me out a 1, 0 state. And this is what the truth table looks like for the controlled NOT gate. Now, you might look at this, and at least, if you look at the target qubit, this might remind you of a classical gate. So again, if you just look at the input and the output value for the target, this actually is similar to XOR, where you're XORing the value of control and the input value for control and target on the target output. We're going to be talking about this more in detail, but I'm just going to throw that out there. And again, this gate is very important, so we'll be seeing it over and over again. And finally, let's talk about quantum entanglement. So quantum entanglement is a quantum correlation between 2 qubits where the state of one qubit depends on the state of the other one. Okay, let's see, what do we mean by that? So for example, this is an entangled state. Now that we have, this, at least we know what a ket is, we can use the bracket notation. And so, okay, I'm telling you that this is an entangled state, but what does it mean? Well, if I measure psi, I either get 0, 0 as an output with 50% probability, or I'll get 1, 1, so both qubits being 1 with 50% probability. So again, the only possible outputs of this quantum set after measuring it is 0, 0 with 50% probability, or both qubits being 1 with 50% probability. Now, let me rephrase this a little bit. Let's again look at the same entangled state, or what I claim to be an entangled state. What if I only measure the first qubit? Okay, so if I measure the first qubit, which is, either here or here. Sorry, try to fix that. Yeah, first qubit is this one. So if qubit A, or the first qubit, is 0, then the quantum state of qubit B is immediately set to 0. And vice versa. If qubit A, if I measure qubit A and I get a 1, then the quantum state of qubit B is immediately set to 1. And this is regardless of how far apart these qubits are. So, you can be like, one of the qubits can be on Earth, the other one can be on the edge of the galaxy. And as soon as you measure the state of one of the qubits, it breaks, or it collapses the superposition for the other qubit immediately, faster than the speed of light even. And this artifact was something that boggled Albert Einstein a lot, actually, about when it comes to how does this entanglement and how does quantum mechanics actually not violate relativity? Well, turns out it doesn't. We're not going to go into detail as to why, but this is something that's spooky. That regardless of the distance, as long as you have this entanglement, your qubit states will depend on one another, and measuring one of them will, directly or instantaneously influence the other qubit. And again, entanglement is something that we're going to see throughout the course, and we're going to talk more about. But some of the applications are quantum teleportation, quantum cryptography, superdense coding, which we're going to talk about in detail, and also in general, quantum computation. And one item that we think is super cool, of course, is this quantum teleportation. So for those of you who might have seen Star Trek, or I'm sure it's probably featured in a bunch of other shows, people teleport between starships, between planets, left and right. So what does teleportation mean, actually? So teleportation is transferring information and matter from one point to another without actually physically moving it there. So, I can be, again, on two edges of the galaxy, let's say, and I can teleport, the state of a qubit, from one edge of the galaxy to another without having to, take that qubit and move it all the way. Now, this is almost magical. This is the stuff they see in science fiction. But turns out that this is actually possible in quantum mechanics and in quantum computing. Now, there are caveats involved, of course, because it is with science, but there have been demonstrations of quantum teleportation for 1 or 2 qubits. It gets a little bit trickier / impossible when if you want to teleport the whole person. But things you can teleport the quantum state of at least 1 qubit, and we've done that. Okay, and then the next question is how do you create entanglement? How do you actually make it such that the state of 1 qubit depends on the state of another qubit? So we have this circuit here. I'm not going to exactly go through why the circuit creates entanglement. This is something that we're going to wait on a little bit and cover later on in the course. But I just wanted to, again, flash this quantum circuit here, and then go to the IBM quantum experience and see if this is actually what happens. Okay, so with that, I'm going to switch from my presentation to the quantum experience again. Okay, so what I had over there was I'm starting with 2 qubits in the state 0. So, okay, I have 1 qubit here, and I need to add another qubit. Let me get rid of these hot modes first. Okay, so here I have 2 qubits, Q0 and Q1, and well, let's wait for things to update here. very slowly. Okay, I don't know what's actually wrong with the quantum experience right now. Try refreshing the page. Okay, that might be a little inconvenient. But anyway, so we start from the 0, 0 state. Now let's, okay, so still the measurement probability in the state vector is a little bit broken. So maybe I'll just try to run this on hardware directly. Okay, so the circuit that I showed you, we start from the 0, 0 state, then we apply a Hadamard gate. We put the top gate, top qubit in a superposition of 0 and 1, and then we apply a C0 in between the two. And then what I'm telling you is that, like, what I get out afterwards is oh, amazing. Okay, that actually worked. Is an entangled state. Okay, maybe let's take a hit on the second measurement for now. Oh, no, okay, perfect. Okay, so here, what the simulator is telling us is that, we get the state 0, 0 out with 100, with 50% probability, and we get the state 1, 1 out with 50% probability. So if qubit 0, or sorry, if Q0 we measure Q0 to be 0, then Q1 is also 0. And if we measure Q0 to be 1, then Q1 is also 1. So the state of one qubit depends on the other. Because if you just like decide to throw away one of these qubits, and all of a sudden you just have a classical coin flip on your hand. So you need both qubits to understand what's happening in the system. And that is actually something that's unique to entanglement. Okay, so with that in mind, let's try to run this on an actual hardware, an actual quantum chip, and see what we get as an output. Okay, let's try. Moment of truth. Let's see if we were wrong or not. If quantum mechanics is broken or not. Okay, amazing. So we almost get 0, 0 and 1, 1 with 50% probability each. So quantum mechanics does work. Quantum computing does work. Now, you might be asking me or yourself, why do we have, why are we getting these other states, with some probability? And that could be attributed to the quantum error or the error in general that's present in our quantum computers. So it can either be a measurement error, where the qubit is in state 0 and we're accidentally measuring state 1, or it can be, all sorts of bad quantum things that can happen in our quantum circuit. We're going to be talking about those in detail later in the course, but just know that again, like these probabilities are very close to where they need to be. And yep, okay, let me switch to my slides again. So again, we ran this quantum circuit on an actual quantum computer, and we showed that it does generate an entangled state, where the state of the first qubit depends on the state of the second qubit, and there's no other way of describing your system. Okay, So with that, we conclude the lecture for week 2. So we have some announcements, of course, and I don't know if Kira wants to do the announcements, or should I?
I can do them. So first off, in your lab this week, you will be covering math high school review. Again, this is math that you're going to need to be able to do more of the advanced quantum problems that will come up later in the course. The homework will be available on Discord in the course announcements. We will send it, it will also be in the QxQ announcements. Again, the math will cover, or the homework will cover a math review. You will be submitting your homework for both last week and this week, this upcoming Saturday. You will be submitting this on Canvas. We will provide more updates about this on Discord later this week. So in terms of important notes, you will be sent an email with your Canvas login information later this week. No one has been sent Canvas login information yet, so please do not ask us about Canvas information yet. There will be no more lab changes. Again, we changed over 2,400 labs from individuals this past week. The deadline was yesterday. The only exception we will make is if you have not been assigned a lab yet, email us immediately. We will only be assigning labs up through today, and then you know, we will withdraw you from the class if you have not applied for a lab yet. Also, going forward, it is very important you respect the deadlines that we have in place. It creates a huge administrative overload otherwise. Again, we've mentioned this many times, but this keeps on happening. So please do not be sending individual messages unless you're instructed to do so by an admin. Please make sure you're posting in Discord and Piazza first if you have a question, and then email us if you still can't figure it out either by an admin or a peer. And we do have live verify open on Discord. If you've not been verified yet, today at 6 p.m., this should actually just be Eastern time, will be the last chance you can get verified. And again, just 2 last things. One, we want to make sure, please make sure you're adhering to the code of conduct and that you are being respectful of others. The Discord channel, first and foremost, should be used Discord channel should be used for focusing on quantum and building the community. So please make sure that you are being respectful and making sure everyone feels safe and that the environment feels inclusive. And then the last thing, if you want to learn more about how to use Discord, Piazza, and Canvas, please stay on. We'll be giving a 5-minute break, and then we'll be getting started with a tech platform tutorial by our 2 co-tech leads. So if you're interested in learning more, stay on. We will get started in 5 minutes. So at 4:03 p.m. Eastern time. So just stay on and we'll go over how to use these different platforms. Again, we want to thank you all so much. We are so excited for you all to be here and be a part of this. I hope you're as excited as I am learning about things like quantum teleportation, which literally blows my mind that this is even possible. So thank you again. Amir, do you have any final words for the lecture?
Yeah, absolutely. So again, I hope you guys found this lecture to be exciting. We're just scratching the surface here of what we can do with quantum computers. And there's so much more. So again, this was just to give you guys a taste for what's to come. And we will have a lot of your questions answered throughout the course. So just stay with us, and we're very excited to have you on this journey.
So again, everyone, if you're staying on, we'll be back in about 5 minutes to go through a tech tutorial of the different platforms we're using and answering your questions, so we make sure you're getting everything out of the platforms that you need to be.